Okay, today we will look at BJT characteristics, regions of operation, biasing, forward active model, and a couple of examples. So let's first discuss in brief this slide. Okay. In a BJT, we have base in the middle, emitter on the outside, collector on the outside. So we have emitter-based junction and we have a collector-based junction. Depending on the junctions being forward bias or reverse bias, we have 4 different modes of operation. Typically, we say it's only 3 different modes of operation because this reverse active region is forbidden, or is at least we don't want the transistor to operate in reverse active region. No good can come from it. There's no application. The transistor is completely off. And that occurs when the emitter-based junction is reverse bias and the collector-based junction is forward bias. Now, the thing to keep in mind is, unlike an FET or a MOSFET, a BJT is not symmetrical. Okay? An FET or a MOSFET, you have a channel and you have 2 regions surrounding the channel. The source and the drain can be interchanged. In a BJT, that is not possible because of the physical construction. The emitter is the smallest structure out of the 3, but it is the most heavily doped. The collector is the most lightly doped. Collector is the biggest region physically, but the most lightly doped region. So if you reverse it, if you reverse bias the emitter-based junction, there are no charge carriers flowing through the emitter to the base junction. Okay, so there'll be no current flow at all. Transistor will be completely off. So reverse active is not a region where we want a transistor to operate in. Where we actually want it to work is the forward active, or simply known as the active region. And that occurs when the emitter-based junction is forward bias and the collector-based junction is reverse bias. When the emitter-based junction is forward bias, all of the charge carriers that are present in the emitter are injected into the base region, and current flow can occur. In this region of operation, the transistor works as an amplifier. It works as a voltage amplifier, a current amplifier, and a power amplifier. In fact, most of the amplifiers that we use nowadays always has transistors working in the active region. Then we have the cutoff and saturation regions. In the cutoff region, both the junctions are reverse bias. If both junctions are reverse bias, there's minimal current flow, and we say the transistor is cut off. In saturation, both junctions are forward bias. When both junctions are forward bias, there's maximal current flow, and we say transistor is completely on. By itself or by themselves, they are not much used, but when you combine both of those together, we can use them to build digital logic circuits. Cutoff represents logic 0. Saturation would represent logic 1, low and high. And so in the active region, we build analog amplifiers or analog circuits. And in cutoff and saturation, we build digital logic circuits, which is what 307 is. In 307, you will build circuits using BJTs and FETs, where they would be operating either in cutoff or saturation. In 308, you're working with analog circuits, where again, you would build circuits using BJTs and FETs, but they'll be working in the active region. And 409, electronic design, mixed signal electronics, where you put everything together. Okay. So from here, let's talk about transistor characteristics. Actually, I'll come back to this slide later. Let's talk about characteristics. So we have transistor output characteristics. If you recall from MOSFETs, FETs, from the diodes, when we talk about characteristics, we are talking about a current as a function of the voltage, meaning current is on the y-axis, voltage is on the x-axis. In a transistor, in a BJT, collector is where we usually take the output. Okay. So when we talk about output characteristics for a BJT, we are stating that it's a plot of the collector current IC right here. I don't know why it got cut off. IC as a function of the collector to emitter voltage VCE. Okay. So it's collector current as a function of the collector voltage. Now, compared to an FET, we would call this as the what region? Pinch off or saturation region, right? In a BJT is known as the active region versus pinch off or saturation in FET devices. And what was known as the linear or the triode region in an FET is referred to as the saturation region. And as it so happens, as what usually happens in life, even if the naming convention does not accurately describe a quantity, it becomes the norm. Okay, so it's not saturation, but it's been called saturation, misnomer, and that's when the transistor is fully on. Okay, so as I was saying, we have the saturation region on the left, and then right here is the cutoff region. And that's where we have minimal current flow. Okay, that's the cutoff region. And then we have the reverse active right here, which is something we don't want to be, right? We don't want to be in that reverse active region. There's no application for a transistor, but students should still be aware of the reverse active region, especially when you're designing or building your own circuit. If nothing is working, more likely than not, you might be inadvertently in the reverse active region. Okay. All right, let's talk about the biasing modes. Well, what is bias? Electrically speaking, not philosophically. What is bias? Bias is the constraint placed on the device by the external circuit. Right? Bias is the constraint placed on the device by the external circuit. We apply some voltages to force the device to a specific point of operation. Remember Q point, right? We set a fixed operating point for our device by using external energy sources, external resistors, to force that device to operate within a certain region or a certain fixed point. So we can describe it as external circuit constraints. External circuit constraints. We just spoke about the characteristics right here, right? If you look at the expanded characteristics, it's on the next slide. Again, VCE right here, IC on the y-axis, and we have a load line that intersects these characteristic curves. If we want or wish to use the BJT circuit as an amplifier, we want it to operate in the active region right here. So then the external circuit biasing must be such that the Q point should stay within this active region. If you want to use it as an amplifier and the Q point drifts away towards the saturation region, it's not going to work, or it will work, but very poorly. Does that make sense? Right? On the other hand, if you want to use it in the saturation or cutoff region, and the Q point gives drifting away into the active region, again, transistor is not going to work as a switch. So biasing is very important because it forces the transistor, the BJT device, to work in our desired operating region. Okay. Now, when we talk about biasing, we typically talk about DC voltages. Okay, DC voltages. And at this point, I always like to remind students, can you explain how an op-amp works, or what is it that an op-amp does in general? An op-amp takes the input signal, amplifies it, and sends it to the output. Op-amps are known to have gains, infinite gains, but in inverting or non-inverting configuration can have tens or hundreds, right? So if you apply 1 volt with a gain of 100, you would expect 100 volts. But that's not really true, is it? Energy cannot be produced out of thin air, right? So the op-amp requires biasing voltages. DC biasing voltages are applied to the op-amp, then it takes the AC input, mixes it or adds it to the DC source, and sends it to the output. The reason I bring up op-amp is because op-amps are nothing but differential amplifiers created using BJTs. Okay, so op-amps are nothing but differential amplifiers created using BJTs. So a BJT in the active region works as an amplifier by taking tiny AC signal and adding it to a DC source. DC source, of course, could have any value. That comes from our biasing circuit. This would be VDC. This would be the AC signal, and it results in an amplified output. I like to state this in 2 ways, and both ways work. Meaning the BJT or the amplifier is taking the small AC signal and adding the energy of the DC source to make it larger. Or the other way to explain it is it takes the DC, it's a flat DC line, and gives it the shape of the AC input signal. Does that make sense? Yes. No, it doesn't shift up. So what you are referring to is the point being made is about DC offset. And that would be a very valid point. If we look at something like this as an illustration by itself with no context, we would say, yes, we are applying a DC offset to our AC signal. But I'm just making a very simple analogy in how an amplifier or an op-amp would work. It would take a tiny AC input signal and it amplifies it, but that energy for the amplification does not come from thin air. It comes from the DC biasing voltages that we apply to our circuit. And that's why biasing is important. Okay, so it takes the energy from the DC biasing voltages and applies it to the small AC input signal. So I guess it'd be more accurate to state that the DC energy source takes on the shape of the AC input signal. And that is actually what happens. And we will see that when we get to CE amplifiers. Okay, that's the lab for next week. That's the lab for next week. Okay, so that was for bias. So depending on the mode or the terminal connections, we have 3 modes. We say the BJT can be connected in either common emitter or common base or common connector mode. Okay, common collector mode. Let's start with the most common, which is the common emitter. So in the common emitter mode, we have the emitter terminal that is common to both the input as well as the output. So the way we typically draw transistors, whether they are PNP or NPN, is like this, with the input on the left. Okay, input on the left. That's your base, that's your emitter, it's a collector, and that's your emitter. So inputs on the left, applied between the base and the emitter, and the output is on the right, collected between the collector and the emitter. And since the emitter is common to both the input as well as the output side, this configuration is known as the common emitter configuration or the common emitter mode. Okay. This is part 2 of the lab this week. Okay, students who already finished the lab yesterday, you already know that, but students who have the lab tomorrow, this is what we're going to do tomorrow, obtaining the characteristics of a common emitter configuration. And in part 1, we're obtaining the characteristics for a common base configuration. Common base, as the name suggests, has the base terminal common to the input as well as the output. And so that would look something like this. Emitter and base at the input, and then collector and base at the output. Okay. And then we have the least common, which is the common collector mode. You'd be hard pressed to find it in any modern textbook too. Would not be discussing common collector modes. But they would look something like this. Oh, actually the other way around. Oh, well, let me just try it. It's a little bit incorrect, but I'll leave it as it is for now. And this will be the common collector. The emitter and the base will be switched. So common emitter and common base are the most popular ones. Common emitter is the most popular because there are several reasons, but 3 of the main ones are it has very high input impedance. Low output impedance, which is very critical if you are trying to use it as an amplifier. And it is easy to bias it with a single power supply. So you can bias the input and the output side with only a single supply. Anyway, in the lab this week, you're simulating you're experimenting with the common base and the common emitter modes. And the next week, you're designing a common emitter amplifier. P1. Characteristic. And let's look at the transfer characteristics. Transfer characteristic, again, as the name suggests, how is the input being transferred to the output? Okay. So the output is the collector current. Input is the base emitter voltage, VBE. So IC as a function of VBE. And we saw something similar for the FETs also. So when you plot the collector current IC as a function of the base emitter voltage VBE, you obtain a plot that is very similar to a forward bias PN junction or PN junction diode. Okay, very similar to a forward bias PN junction diode. I'm gonna try and. Okay, so it looks like a forward bias PN junction. If you plot the collector voltage, collector current IC on the log scale, you get a linear line with a slope of 1 decade for every 60 millivolts drop. Okay, slope of 1 decade for every 60 millivolts, or a change of 60 millivolts for every decade. So every decade change in the collector current, voltage drops by 60 millivolts. Okay, one of the models that we're going to look at is the forward active region circuit model. And in the active region, now the book and the notes will say forward active to distinguish between reverse active, but reverse active is not under consideration for the most part. So if you hear just active region, more likely than not is always referring to the forward active region. Okay. So in the forward active region, or simply the active region, the base emitter junction is forward bias, right? So it behaves like a forward bias PN junction with a voltage drop of VBE across it. On the output side, we have constant current flowing from the collector to the emitter terminals. So if you look at these characteristics, the values for these current in the active region is almost a flat line. It's almost constant, right? And when current is constant, it's a current source, right? When the output current is constant, you can model as a current source. Also, as IB increases in value on the input side, the slope also increases. There is a reason for that, and that'll come in the next few slides. You can see the slope increases as we go higher up. Okay, so on the output side, we have the collector current IC. IC, of course, is beta IB. And it's a function of VBE. So we can describe this model. Or using this model, we can describe the BJT as a voltage controlled current source. I'm assuming at this point that you all, well, if not remember, at least came across this in 113 last year, right? So again, the reason it is a current source is because the output current IC is constant or near constant, a flat line, and IC is controlled by the input voltage VBE on the input side, base voltage on the input side. Hence, we can describe the BJT in this region, in the active region, as a voltage controlled current source. Okay, voltage controlled current source. So this model is very useful in many analysis cases. Okay. All right. And then this simply is replacing the diode with a constant voltage drop model of 0.7 volts. Okay, 0.7 volts. That's all it's doing. So let's look at a couple of examples in the forward active region. Okay. In this example, we have a BJT with two biasing sources, VCC on the output side, and a current source of 100 microamps on the input. Okay. We are given a couple of values. One is IS, the saturation current, 10 raised to minus 16. And then we have alpha as 0.95. 0.95. Alpha, again, as a reminder, is the ratio of the collector current to the emitter current, IC, divided by IE, right? It's not quite equal to 1, but it's very, very close to 1. Typically, it's always 0.99 or 0.999. Okay, 0.999. Also, if these values are not given, then you can simply assume. Okay, 10 raised to minus 15, 10 raised to minus 16 is a good value for saturation current, and 0.95 to 0.99 is a good value for alpha. 0.95, I would say, is on the lower side, on the lower end. Real life transistors, it'd be much higher. Okay. All right, so then we need to find all the remaining. We have given IB, IC, IE, VBE, and VBC should all be determined. Okay. So let's begin. We will assume that this is room temperature operation. And so VT is not given to us, but we will assume it to be 25 millivolts. All right. Let's look at the input side. What do we see? On the input side, we have a current source, 100 microamps, that is going into the NPN transistor. So current is flowing from the base to the emitter. So it's forward biasing the base emitter junction. Since it's forward biasing the base emitter junction, there are only two choices. It's either in active region or it could be in saturation. My default go-to is always to choose as active. Okay. So I typically assume that it's in the active region, then I perform my analysis, verify my values. If it's not, more often than not, turns out to be correct. If it's not, then you go back and make a different assumption. Okay. But right now the current is going in, it's going into the base through the emitter. And so it's more likely than not forward biasing the base emitter junction. So I am going to assume that the BJT is in active region. So active region of operation. Okay, active region of operation. And if you're making that assumption, then it logically follows that the base emitter junction is forward bias. And so VBE would have a voltage drop of 0.7 volts. So we can assume active region, and hence from there, we can logically conclude or logically assume VBE is also 0.7 volts. So far, so good. Then we have VC, the collector voltage, as 5 volts coming from the VCC. VC is equal to VCC, which is 5 volts. And hence, I can write VBC is VB minus VC, which is 0.7 minus 5, gives me 4.3, actually minus 4.3 volts. Minus 4.3 volts. Excuse me. Okay, minus 4.3. And since that turned out to be negative, that the collector base junction is reverse bias. So reverse bias, that means it definitely is in forward active region. So IC in forward active region would be beta IB. And beta is not given to us, but alpha is. And so we can plug that in. So this would be alpha over 1 minus alpha times IB. Alpha is given as 0.95. So 0.95 divided by 1 minus 0.95. And IB is, of course, 100 microamps. So 0.0001. And that gives me a IC value of 1. Oh, where's my IC? 1.9 milliamps. 1.9 milliamps. Okay, 1.9 milliamps. So now we have IB and we have IC. We can apply two equations to find IE. Alpha is the ratio of IC to IE. We can apply that and directly find IC, or sorry, directly find IE. Or we can also apply the other equation, which is beta plus 1 times IB. And so this would be, this is actually equal to 19. So this would be 20 times 0.0001. That gives you 2 milliamps. IE would be 2 milliamps. Okay. And from there, lastly, we can find VBE and VBC. VBE was an assumption at the beginning, but now that we have the value for IC, we can actually calculate it by plugging it into the equation. And so VBE would be equal to VT times log of IC over IS. 25 millivolts, 0.025 times the log of IC, which would be 1.9 milliamps, 0.0019 divided by IS, 10 raised to minus 16. And this comes out to be very close to our assumption, 0.764 volts. 0.764 volts. And once we have VBE, we can find VBC. VB minus VC, that is 0.764 minus 5, and it's minus 4.24 volts. Okay, just slightly off from our assumptions. All right, questions? Well, 13 minutes left. Okay, let's look at example 2. In example 2, we have biasing voltages, but now we have two resistors in there. Okay, two resistors. We have a collector resistor and what should be RE. RE, emitter resistor. Okay. There is no biasing connected to the base. Base is connected simply to ground. And then we are asked to find the Q point for this circuit. Okay. What does it mean when the question says find the Q point for this BJT? For a diode, it simply means diode voltage and the diode current. What does it mean for the transistor? Any guesses? Turns on. But what quantities do we need to find? So IC and VCE. Net Q point for this means we are talking about the output of the transistor, where we want the transistor to operate. And so IC and VCE. The point on the load line where the transistor is forced to operate by the external circuit. Right? Okay. So what else is given to us? We are given the values for beta F. We're also given the beta for the reverse active as 1. And then nothing else is given. But when we begin our analysis, again, we want to make an assumption whether it's an active region or cutoff or saturation. So if we look at the circuit and extract information, what do we see? Base is connected to 0 volts. And emitter is connected to negative voltage. And it's an NPN transistor. So the base is P-type, emitter is N-type, meaning the base emitter junction is it in forward bias or reverse bias? NPN transistor. For a PN junction to be forward bias, the P-type material must be at a higher voltage level than the N-type, which is true in this case. 0 is higher than -9. And so VBE is forward bias, or the base emitter junction is forward bias. And hence my assumption is active region of operation. Okay, active region of operation. And if I'm assuming active region of operation, then I can use the forward active model and redraw the circuit. The forward bias diode and a dependent current source. Okay. So now if you want to find these voltages and currents, go back to our three theorems, 3 equations. Ohm's law, KVL, KCL. Okay. And this is going to be the typical approach for most of these circuits. You apply either KVL or KCL to generate equations. Right now we have these voltage sources. So KVL makes the most logical choice. And when you apply KVL on the input side, we have these voltages. On the output side, we have these voltages. In this model, we can say we are applying KVL in this loop. And the output side, we are applying KVL in this loop. think I made it worse. Okay. All right, so let's apply KVL on the input side or the input loop. How many voltages do we see? VBE, and then the voltage drop across RE, the emitter resistor, and then the voltage VEE. Okay. So apply KVL to input loop. We obtain an expression VBE plus VRE, and then it'll be minus VEE. Voltage equal to 0. VBE, let's assume to be 0.7. VRE would be IE times RE, so 80 to 100 times IE, and minus 9 should sum up to 0. Therefore, IE is 8.3 divided by 80 to 100. 1.01 milliamps. 1.01 milliamps. If IE is 1.01 milliamps, we can find IB on the equation. IE and therefore IB is IE 1.01 times 10 raised to minus 3 divided by 50 plus 1. That gives me 19.8 microamps, 10 raised to minus 6. Okay, it's 1.01. Yeah. And then from there, I can find IC. IC is beta IB. So that comes out to be 0.99 milliamps. So you found one value, one more to go. But I want you to take a pause and take a look at the values for the three currents. No, IE, sorry. Yeah, that's, yes, it's just IE. So here, let me write better. No, it's good. IE, IB, and IC. But if you look at the three current, the values, what do we see? IE should be the largest current. Right? IE should be the largest current because IE is equal to the sum of the base and collector currents. So IE must be the largest. That's the first thing. Second, IC should be very close in value to IE. Very close, but not larger or not the same. This is not an FET. In an FET, the gate current IG would be 0. In a BJT, IB will be very, very small, but it will be a positive value. Okay. And so IC would be very close in value to IE. And the ratio of IC to IE is alpha, which, as I stated just a few minutes ago, is about 0.99, very close to unity. And then IB is by far the smallest value, and it's typically in microamps. Okay. At the most, you might get 10 raised to minus 6 or 10 raised to minus 5. Maybe some worst cases you might get 10 raised to minus 4. But if it's in the milliamp range, then there's some error in your calculation. Okay, so you have to keep these three things in mind. IE is the largest current, should have the largest value. IC should be very close in value to IE, and IB should be about approximately 1,000 times smaller than IE and IC. Okay, so if it doesn't align with these 3 points, then there might be an error somewhere in the calculation. All right, let's quickly find VCE by applying KVL on the output side. So KVL in output loop, I would get VCE is equal to VCC minus ICRC minus VEE, and therefore VCE is equal to 9 minus 0.99 times 10 raised to minus 3 times 4,300 plus 0.7, and therefore VCE is equal to 5.44 volts. 5.44 volts. So the Q point is 0.99 milliamps and 5.44 volts. The value of VCE also tells us that it is in the active region. And I'll wait for 30 seconds and I'll bring up the characteristics to make that point. Okay, so VCE is 5.44 volts. That indicates it should be in the active region of operation. All right, we're almost out of time. Just quickly, I want to point this out. So in the characteristics, right here, what do you see? When the transistor is in saturation, VCE value is typically 0.2 to 0.4 volts. Okay, in saturation, VCE is less than VBE. If VCE is higher, then you can see it's around somewhere here, then it's an active region. Okay, and so that's also an indicator that our assumption is indeed correct. Okay, all right, for the next one, 5.44 volts. Okay, let's end class here today. I think we've gone over a minute over time. So we'll pick up here again on Friday.